Our next speaker is Tuanan Lourenço. He is a postdoc at IQSC.
Good morning. So today I'm going to talk about our project called Molecular Dynamic Simulations of Ternary Electrolytes at Lithium Metal Interface. This project was made in collaboration with Professor Daniel Brandel and Dr. Márcio Badi from Uppsala University in Sweden, and also Professor Luciano Costa from Universidade Federal Fluminense, UF, in Niterói, and also my postdoc supervisor, Professor Juarez da Silva. I am part of the QTNano battery team. We are starting a QTNano battery team now. So for now, we have me as a postdoc, Giovanna Fardini as an undergrad student, Professor Luiz Gustavo Dias from USP Ribeirão, and Professor Juarez da Silva. We are closing the project about the lithium metal batteries, and we are moving to sodium-ion batteries. I'm also doing a project inside the P16 projects about molecular dynamic simulations of cerium oxide nanoparticles, in which we are doing some simulations to do a simulated synthesis of these particles, and I'm going to show this in the poster session. So before we go to the results, just a short introduction about lithium-ion batteries. So this is a schematic view of an lithium-ion battery. So here we have the anode, graphite, and the cathode based on transition metal oxides, in general cobalt, and the organic electrolyte. This is very similar with the lithium-ion batteries that we have today, and they are very similar with the first lithium-ion battery. So in these 30 years that we are using this kind of battery, the performance increased a lot, the price decreased, but the chemistry of the battery is still pretty much the same. And for now, we have a problem. Since that these batteries are close to the maximum performance that it's possible, we have to change something here to increase the performance. Because right now, we have electrical vehicles, industrial applications, so we need high performance batteries. One simple way to improve this performance is just change the graphite anode by a lithium metal anode. So if you look in here, we see that the lithium metal based batteries have a higher performance than all batteries that we have in the market. So what is a lithium metal battery? So here's a chart. So here is the cathode, that is transition metal oxide also, and here is the anode. So this is lithium metal anode. So in the lithium ion battery, the battery works with the intercalation of the ion metal in the cathode and in the anode. But here, there is no intercalation in the anode. We have the stripping and plating of the lithium ion in the metal surface. And because of the redox potential of the lithium, we have a very good performance. But lithium metal batteries have some major drawbacks. Two drawbacks, like solid electrolyte interface information and the lithium dendrites growth. So as I said, we have the lithium ion in the electrolyte. So we have the deposition of these ions in the metal surface. But we also have here undesirable reactions between the electrolyte and the metal surface. And these undesirable reactions generate this solid electrolyte interface. That is a solid interface that decrease the mobility of the lithium ions from the electrolyte to the metal surface and block the deposition of the ions. So this decreases the battery performance, and also this solid electrolyte interface influences the dendrite growth. So since that we have the deposition of lithium ions in the metal surface, if this deposition is not like homogeneous, we have the formation of the dendrites. It's similar if we have a bunch of lithium ions above themselves. So there's the formation of this something like a tree of dead lithiums or a branch that grows into the cathode. And once the time that these dendrites reach the cathode, we have a short circuit and the battery explodes. So this is a not safe battery, but there are some ways that we can avoid the formation of these dendrites and the solid electrolyte interface. If we choose the proper electrolyte, we can control this. So some electrolytes, like polymers electrolytes and solid electrolytes, can block the dendrites growth using the Young modulus or the elastic modulus of the electrolyte, but also ionic liquids can create a kind of a passive layer in the metal surface that help the migration of the lithium ion from the electrolyte to the surface. So we have to understand how this interface between the electrolyte and the metal surface is. So this is our main goal here, understand the interface, see what is the morphology of this interface, how this affects the lithium mobility, and how this can affect the electrolyte performance. But what kind of electrolyte we are studying here? We are studying ion liquids based electrolytes. So as Rafael said, ion liquids are very good electrolytes. We have here the cation and the anion. But ion liquids have a problem. When we have lithium into the ion liquid, lithium starts to coordinate strongly with the anion that result in some structures like this that we can call clusters or aggregates. And this is very stable and slow. So there is a decrease in the ionic mobility of the lithium, a decrease in the ionic conductivity, and a decrease in the battery performance. One way to avoid this is adding here a neutral molecule that can change the lithium environment and decrease this interaction, so weaken this interaction and increase the lithium transport. So this is why we are going to look to ternary ion liquids-based electrolytes. But in our case, our neutral molecule is a polymer, PO. PO is a good additive in electrolytes because PO can coordinate in a weak way with lithium, and also PO has a structure that we call helix structure that's very similar to DNA structure that creates some kind of channels inside the electrolyte and improve the lithium dynamics. So we have three systems. First one based on the imidazolium cation, triazolide anion, PO and lithium. Second one, imidazolium cation, TFSI anion, PO and lithium. And third one, the phosphonium cation, TFSI anion, PO and lithium. So if we look to our three systems, we can see some similarities between them. So if we compare 1 and 2, we can see that we are changing this small and flat anion for this larger and flexible anion. So here we can understand the influence of this type of anion in the system. Same here, we are changing the flat and the small cation by a more large and spherical cation in the systems. So with these three systems, we can understand the influence of different ion and liquid ions in the system. So we run MD simulations using GAF force field. We have 200 nanoseconds in the NVT ensemble. This is our box. So we have the electrolyte, the electrode, so two lithium metal surfaces that we are using Lennard-Jones to simulate the interactions between the electrolyte and the lithium metal. The charges in the lithium metals are 0, and they are kept constant in the same position in the whole simulation. So first here, we have the interfacial aggregation formation. So system 1, system 2, and system 3. So here we have the number density distribution for all particles inside the box. So this is the z-axis of the box. The dashed lines are the metal surfaces. So if we look too close to the metal surface, we can see that all the particles have some kind of interfacial aggregation close to the metal surface. So we can see that in all the three systems, we have the formation of layers close to the surface. And if we do a zoom here to see how is this distribution, we can see this. So these three plots are just a zoom in the interface region from the previous plot. When I say interface region, I'm talking about the lithium metal surface and all the particles that within a 1 nanometer cutoff from the surface. So comparing 1 and 2, we see a very similar behavior. So these are the system based on the imidazolium triazole and imidazolium TFSI. So just comparing these two, we can see that changing the anion from this guy for this guy doesn't change too much the distribution of the particles in the systems. We have the first layer that contains the anion, cation, and PO, and same here. So here and here, we can see that we have some indicatives of the formation of the passive layer that the ion liquids can create in the metal surface. But when we compare 2 and 3, so imidazolium and TFSI, and phosphonium TFSI, we can see that when we change the cation, we change a lot the distribution of the particles in the box and close to the surface. Here in blue, this is the cation peak. So we see here a more straight peak, very high density. But when we look here, we see a more broad distribution and a smaller intensity. Why this happens? This happens basically because of the size and the shape of the cations. So this is imidazolium, so we have a ring, so a planar cation, and because of the ring, imidazolium can go too close to the surface and adopt some kind of a parallel stacking to the surface, so the interaction of the layer is something like this. But here in the phosphonium, phosphonium is bigger and more spherical, so we have something kind of a random distribution of the cation close to the surface. That means that we have the broad distribution here. And also, this random or more broad layer here also influences the distribution of PU close to the surface. If we look to the two systems that we have in imidazolium, we see a sharp peaks of from PU close to the surface and higher densities than in the bulk. But here, when we have phosphonium, we don't see too much difference between the bulk and the interface region. So with this guy, with the phosphonium, we can decrease the number of PU and also increase the populations of lithium close to the interface, because here the peak is closer than the other two systems. So to see what is the lithium environment in the interface region, we have the lithium solvation shell, so radial distribution functions. So in this side, we have the imidazolium triazole system, and in this side, the phosphonium TFSI system. First row is the interaction between lithium and the anions, so lithium and triazole, lithium and TFSI, and second row is the lithium and the ether oxygens in PU. So if we look here, in black is the interface region, and red, the bulk region. So going from bulk to the interface, we see an increase in the coordination numbers of the anions around the lithium. That makes sense, because if we have a higher density of anions close to the interface, we have more anions around the lithium. And if we look here to the RDF peaks, we see an increase in the intensity of these RDFs. So this means that this interaction is well structured in the interface than in the bulk. So we have a more ordered system close to the interface than in the bulk. But when we look here for the interaction between lithium and the ether oxygens in PU, we see a different behavior. So going from bulk to the interface, there is a decrease in the coordination numbers of PU around lithium. That also agrees with our density distributions. And if we look here in the phosphonium system, we see a huge decrease in relation to the triazolide system. This is because when we look in the density distribution, we saw a smaller peak in the interface than in the imidazolium system. And also, if we look here to the coordination numbers that are close to 6, we can see that we have some indicatives of the formation of this structure that we call crown structure. I said in the beginning that the PO can adopt like a helix structure, so it's like the DNA, and inside of this helix structure, the lithium can go and back, so this increases the transport of lithium in this system. So here we have dynamical and polymer properties. So we have self-diffusion coefficients for all ions in the system. We don't have for PU because PU is too slow, so we're just looking to the ionic mobility. And we have radius of gyration and head-to-tail distance for PU. So if we look to the polymer properties, nothing too much interesting here when we change the systems. But if we look to head-to-tail distance in the interface in the book, we see some effects. At the interface, PU can adopt a more flat or extensive conformation because we have more structured systems in the interface. So PU change the conformation close to the interface. But when we look here to the self-diffusion coefficients for lithium in the interface region and in the bulk region, we see interesting behavior. If we look to the system 1, we have here the higher diffusion coefficient, much more higher, more than 4 times higher than in the other systems. But when we look in the bulk, this is different. So we have a different behavior in the interface and in the bulk region. I said in the beginning that the imidazolium cation is planar, so there is a ring, and because of this, the imidazolium cation can adopt a parallel stacking to the surface, and the same happens with the triazolide, because we have the triazole ring, so triazolide and imidazolium can adopt some kind of packing in the structure that creates some planes inside the interface, and this increases the lithium transport. This is a very known behavior in ion liquids in like bulk phase. When we have planar ions in the system, the planes inside can decrease the energy of the diffusivity of the ions in the system. So as conclusion, we have the formation of the interfacial electrolyte layer that is an indicative of the passive layer with these ion liquids that we show here. The size and shape of the ion liquid ions influence the interface morphology and also the lithium ion dynamics. And if we have to choose right now one system to go to the lab and do some tests, I think the imidazolium triazolide is a good candidate to the lithium metal batteries electrolytes. I said in the beginning that we're finishing this work and moving to the sodium ion batteries study. So this is our project, the computational material screening for sodium ion batteries. So we are going to use DFT, MD, AMD, CFD, different computational techniques to study several materials for cathode, anode, and electrolytes in sodium batteries. And at the end of the project, we expect that we are going to create one kind of a multiscale modeling that we can use for sodium, potassium, different alkali metal batteries. And the reason that we are going to look to sodium ion batteries, it's because we have a bunch of sodium in the planet. Sodium is very similar with lithium when we talk about chemistry. And also the components of the battery are very cheaper in relation to the lithium, but we have some problems. Sodium does not intercalate very well with the graphite, and we see smaller energy density in relation to the lithium. So this is why we have to test several materials to find the best candidates and compositions. So we submit this project to FAPESP, and we are waiting for the response, but we already started the initial studies of the electrode materials for sodium-ion batteries with Giovanna, and we are also starting the MED simulations of the sodium-ion batteries electrolytes in collaboration with Professor Luis Gustavo Dias. So thank you very much.
Now we are open for questions.
Tuanan, very nice talk. And very nice talk. And do you intend to use, for instance, transition metal decalcogenides as materials to intercalate sodium?
Yes, in some reports, we can see that the transition metal oxides with chalcogenides are very useful for anodes in sodium-ion batteries, but we have some problems with stability, so we have to check several there. But we have a lot of data about this.
Yeah, that's what I was about to talk to you, because putting a metal in the surface of the decalcogenide can change the relative stability of the phases.
Yeah.
So I think that you should look for platinum-based decalcogenides because they present a non-layered phase. It's a pentagonal phase, so it would be harder for the metal to change the stability of the phase.
Yeah, the major problem in the electrodes with sodium is the phase stability. Because of the intercalation of sodium, there's a lot of changes in the stability, so some damage to the electrode. So yeah, good, thank you.
Okay, thanks for the nice talk. I have one question, one comment. For the first question, for example, on the beginning of your presentation, you showed this picture of these dendrites with these lithium batteries. Okay, this is the problem that happens in the lithium batteries quite so often. But on your simulation, because you are not able to address the problem because you are using frozen lithium metal. Means it is possible to do a performance simulation to mimic the dendrite formation along the simulation?
Yeah. So in the MD with the fixed layers, we could see something like this if we saw like a very large population of lithium close to the surface, can be an indicative of the dendrites. But also I think if we use something like a REACT or AMD, probably we can see the increase of the dendrites because we have better interactions or reactions inside.
But a lot of lithium ions close to the interface. It means they can be homogeneously distributed and not form a dendrite. That is a lithium metal, let's say, basically as a line of metal.
Yeah.
Okay, it's two different things because one's a lithium ion distribution on the liquid that you have there.
Yeah,
There's
yeah.
two different things. Okay, a second comment that I will do for the first, after the first three talks, I would like to see more combination of ab initio quantum chemistry with the molecular dynamics for us to make sure that those potentials that you are using, those results that you are getting are really meaningful. Because you should be able to combine all the expertise that you have inside of the team. Okay, it goes from ab initio quantum chemistry, if you can do a small systems, small cases, and how you can move it to large case systems.
Yeah.
Thank you, Tuanan. I have a curiosity. How far or how close are you from a real lithium anode in your simulation, for example?
We have the problem with the charge in the system because we don't have charge, but we should have some kind of small, very small positive charge to see some like polarizable effects in the surface. So I think we are not close to the real world, but when we compare the results from the density distributions with like images from experiment, the density distributions are very close, but we are also have some problems with the composition of the electrolytes because here we cannot see. So, okay, it's not a problem because in the experiments they don't see the decomposition, but we should add something to see if there is a small decomposition there or not. So for what we are looking here, it's okay. But if you want to see like a more specific morphology or something close, like the charge transferring is not good enough. We have to improve the models.
We have more questions? Seems that it's not the case, so let's thank the speaker once again.